next talk is from Tenstorrent. Our speaker today from Tenstorrent is Ljubisa Bajic, who is CEO and lead architect. And Ljubisa is going to be talking about relegating the important stuff to the compiler. So Ljubisa, you can go ahead and take it away. Thank you.
Thank you, Bob. Hello, everyone. My name is Ljubisa, as Bob mentioned. I'm here today with my colleague Stan, actually, who's co-presenting. And we're going to be talking primarily about the software component of data-centric processing. So some of you might recognize the title of the talk. It's actually an old joke about what the acronym RISC really means. And I find that there are some strong parallels between current times and the coupled advent of RISC processors and optimizing compilers back in the 80s, and that kind of ties into some of the story that we'll be telling today. But before we get into that, I'll do a quick overview of our company and the products that we've been working on. So Tenstorrent has been around for about 4 years. In that time, we went from 3 team members to about 70 between Toronto and Austin now. We're lucky enough to have a team that has worked on all flavors of parallel computers and compilers for them. So shared memory, multi-cores, GPUs, and FPGAs. So in this diverse set of backgrounds is somewhat responsible for the form that our architecture and our products took. So over the years, we've worked on 3 chips thus far. Our first was Drawbridge, an edge-oriented low-power processor, which was taped out as a test chip a couple of years back. Our second and currently most active, development chip is Grayskull. So this is our first production part, fairly large, high-throughput processor that can do both inference and training, and designed to be in the form factor of GPU-style PCI expansion cards. And then finally, Wormhole, which we'll only be getting into our labs early next year. So Wormhole is built around a similar compute fabric to Grayskull, but integrates a GDDR6 memory interface, an Ethernet switch, and 16 integrated Ethernet endpoints. So with that, I'll get back to the actual topic of the presentation, and that's software, and with a bit of an outsized focus on compilers. And in order to frame the discussion of Tenstorrent software, I wanted to spend just a minute or two recalling the co-evolution of computing machinery and compilers thus far. So the first software that bore the name compiler was actually developed by the illustrious Admiral Grace Hopper, so for the UNIVAC 1, a vacuum tube-based machine produced by EMCC a very long time ago. So although the Admiral called their solution a compiler, really was a linker by today's terminology. So whatever you choose to call it, it was the first decisive step away from handcrafting machine code and towards automatically generating it from higher level descriptions. So the first actual compiler capable of taking high-level programs, generating executable machine code, was developed by John Backus and his team at IBM for the IBM 704. So John, of course, is most famous for developing Fortran. He also has his name embedded in the name of Backus-Naur form, so the formalism used to describe programming language grammars. A good deal later, in the 70s, the first parallelization capabilities started showing up in compilers. And these were in compilers from TI and Cray. So primarily in the form of the ability to unroll and vectorize loops for vector machines. So right around that same time, large-scale parallel computing machinery started being widely available. So this triggered, of course, the desire for compilers to be able to efficiently use these new parallel machines. And unlike the progression of compilers to that point, things kind of started getting a little bit tricky there. So it turned out that the problem of generating high quality parallelized implementations of high level code is a good deal harder than the problems that were tackled up to that point in the evolution of compilers to date. The end result here was that compilers effectively abdicated their responsibility in solving their problem. They really ended up sidestepping most of the problems involved in generating efficient solutions for highly parallel systems. So by example, vectorization relied on providing info to programmers, asking them to fix their code really. So this is the programmer in the loop model. On the slide here is shown an example output of Cray's loop mark, which essentially just points out, how well it did with some code and where the programmer should focus to make the code more parallelizable. This worked incredibly well. It trained a whole crew of vector programming savvy programmers, but it wasn't exactly automatic compilation. The communication problem was farmed off to either hardware. So in the case of shared memory machines, this is the coherence protocols and all the machinery that exists there to make it fairly easy for programmers to produce parallel code. Or else it was farmed off to the programmers themselves in the case of MPI, where you had to explicitly describe every bit of communication between nodes. Parallelization was either to be done by programmers, so in more data flow or hardware-oriented description methods, so like writing Verilog, where you're essentially describing the full parallelism of the system, or completely implied, like in CUDA or OpenCL, where you actually write scalar code, and the compiler just sort of interpolates that scalar code into many copies running on different data. So my point here is that compilers actually never solved the problems of parallelism, which put us in a bad position as we entered the era of machine learning, where large-scale computation has become a truly ubiquitous problem, one that many more people are interested in than as short ago as a decade ago. So the problem is still just as hard. Compilers are still struggling. We're still reaching for many of these same old crutches and solutions that were deployed. And with this as a setup on this cliffhanger, I'd like to pass the talking stick to Stan, who's going to tell you how we approach these problems and built our software stack at Tenstorrent. So I'll stop sharing now, and please take it away, Stan.
All right, well, thank you. I'm really excited for an opportunity to talk a little bit about the software progress that we've made in the company. If you've been following Tenstorrent for a while, we've talked a lot about the great computer architecture and hardware that we've produced so far, but the software really came into its own over the last 6 months, where we now have a compiler that's very general, able to take on many different workloads, run them at high performance, and we're really proud of what we achieved, and I'd love to dive in a little bit and tell you more about it. Now, of course, after that big software intro, I've got a summary of hardware architecture slide over here. But I think it's important to understand a little bit about what our hardware looks like, because it drove a lot of the decisions in our software architecture as well. So as Ljubisa's slides showed, we have this massively parallel chip with 120 10.6 processing cores connected with a network on chip that's specially designed for ML workloads. And what that means is that it's really good at scattering, gathering, and multicasting data, which is extremely important for these parallel workloads. Now, if you zoom into each of these 10.6 cores, you'll see some of the kind of common elements that you've seen elsewhere with SRAM and dense math and SIMD compute engines. But we have a couple of things that are a little bit different from others. We have this a very flexible packet manager that's processing incoming packets and producing outgoing packets into this NOC. And I'll talk a little bit later about why that's important. And on top of that, we have these 5 low-power RISC cores that can run a large portion of our software stack at runtime, making a lot of dynamic decisions that are offloaded from the compiler and really reducing the complexity of decisions that have to be made up front. Now, a 1,000-foot view of our software stack probably looks similar to what you've seen in other presentations. One, maybe not so subtle difference is that we have a couple of firmwares running on the bottom, a separate one for compute and one for connectivity, and both actually very complex pieces of software that are making a lot of decisions on the fly, as I mentioned before. And those are the decisions about how we're going to run something, whether we're going to run something at all or skip it, how we're going to move the data around. Even memory allocation is dynamic, really moving a lot of those decisions away from the compiler onto runtime and making things as efficient as possible for any workload that comes into the device. At the top of the stack is integration into frameworks, of course, and we've decided to start with deep integration into PyTorch because it's one of the more popular frameworks, but it also provides a lot of really neat features for us that that we're using. And I'm going to highlight one that I think is particularly interesting, is that PyTorch allows us to interleave instructions between our device and other devices. So while we've developed a huge library of operations that we support, there's always more experimentation going on in the ML world. People are adding new instructions and developing new networks, and we don't want people to be blocked when they introduce a new instruction. We can just fall back onto the CPU, run that there, and then seamlessly come back to the hardware and run at full speed over there. On top of PyTorch, we also have full support for ONNX and TORCHSCRIPT. Both of those give us the ability to export models from other frameworks like TensorFlow and MXNet and so on, and basically run any model that's written there. And the support below it is really pretty much the same as what we have with PyTorch, making it a very general support of all the frameworks out there. But it's really the graph compiler I wanted to spend more time on, because I think that's where the meat of the problem was. And then Ljubisa touched on parallelization. And obviously, when you have 120 cores that you want to utilize, that's not an easy problem. And then if you now pair up, if you put several of our chips together, you're looking at hundreds and hundreds of cores that need to be utilized, and data has to be moved between them efficiently. The other problem the graph compiler needs to deal with is how to manipulate tensor data between instructions. This is something where our unique hardware really shines and hides a lot of this this problem away. And I'll go into more details later. But finally, the last item that the graph compiler has to deal with is, of course, performance. Without it, really, there's no point in running anything else, right? So the compiler's goal is to perfectly parallelize the data transfers with the compute, so that the compute is busy all the time. And for that, it has to efficiently use all the resources available, all the links between the cores, the DRAM bandwidth, the SRAM bandwidth, the SRAM space, and so on. So let's talk about parallelization first. I think this is the part that I'm most excited about, because it is one of the most challenging things, and something that I think we've done a really good job of. We look at parallelization as a kind of a two-step approach. There's a high-level parallelization and low-level. The high level is pictured on the right side of this slide. And many of you are probably familiar with the ideas of data parallelism and model parallelism, which are used in setups with multiple CPUs or multiple GPUs, where you either copy the same model onto multiple devices and run them in parallel, or you shard the design vertically and run each part in parallel on different devices. But we can go one step further, and because we have this flexible array of 120 cores, we can group them into almost virtual devices on there, clusters of cores, if you will, and run parallelism on those. So this gives us a lot of flexibility, where if you have a small model, like for example BERT base, we could have data parallelism on chip, running many instances of BERT. But if it's something different that shards really well, we can divide that up evenly as well. The third thing that we add to the whole picture is the idea of pipeline parallelism, where instead of dividing the model vertically, you divide it horizontally. And where this flexibility with cores really shines is that you can adjust the number of cores that you give to each pipeline stage so that they're perfectly matched, and that every pipeline stage takes exactly the same amount of time to run, giving you full utilization. And this is often the best of both worlds, where you get very low latency and very high throughput. But now that you've divided the workload, split the model onto these virtual devices, you still have to divide up the actual operations onto the cores themselves. And obviously, the more cores you have, the higher the performance is, but up to a certain point. And if you limit yourself to parallelizing instructions one way only, you're going to hit that limit very often. For example, with convolutions, it's reasonable to divide it by filters, right? But if you look at CNN networks, some parts of the network are really deep with a lot of filters, and it kind of divides really nicely. But another part of the network will only have a few filters, and it's much wider faces. And you really need to parallelize that differently if you're going to reach the full potential. So what we actually have is we have 10 different ways of parallelizing every single instruction. And we have a fully automated optimizer that tries all the different combinations and finds the best way to parallelize every instruction to both maximize the utilization, but also minimize the data transfer rate between cores. Now, tensor manipulations are the other problem with a massively parallel design like this. Really, if you look at CPU that's holding maybe a giant tensor in memory, you can implement things like transposes and reshapes and so on by only playing with strides and read order of the data in memory. But when you actually have to move the data around and bring it to the cores, you can't quite do that as easily, and you can run into paying penalties of reordering data, repackaging data, and so on. However, we've built a really flexible packet processor which can implement many of these striding solutions that exist on the CPU. It can take the results of our math engine and read it in many different ways. It can unpack them in many different ways, and when you combine that with our flexible NOC, which can scatter and gather these streams together, you really give the graph compiler the ability to take any sequence of tensor manipulations between two math commands and convert them simply into a read-write order of packets on the network. And that allows us to completely hide these tensor manipulations instructions from the graph and only do the math on the math compute cores fully efficiently. So let me take a step back now and talk a little more high level. We understand that our customers are already running things on devices that they have right now, and that what we provide has to be pain-free and easy to use for them to try it out. And that's why we've built a delivery system through a Docker container that provides all the software, all the libraries, everything is set up in one place. It's almost trivially easy to install it. And as soon as you do, it recognizes one or many Grayscale cards attached to your system or network, and is ready to present that as a one device to PyTorch to start running your things. Now, if you follow Tenstorrent, you know we've talked a lot about conditional computing before, and this is something that we consciously decided to leave out of this presentation and focus on software today. But we still strongly believe that's the future of ML compute. And I wanted to mention that our software stack has an automated flow where we can enable some of these features on already pre-trained models, and basically with push button get tremendous improvements in performance and efficiency. So we'll talk a lot more about that in the coming months. Stay tuned. Generality was a huge part of what we're trying to do with the compiler. We really set out to be able to run anything thrown at it. And right now, I mean, you can see a fairly impressive list of networks that we support. Every single one of these networks is running through the compiler right now. Many of them are running on silicon at very high performance. The others are being brought up as we speak. And I did wanted to show some performance numbers for some of the networks that are coming out of the compiler. The top number is sort of our compiler goalpost that we set by spending a few months hand tuning a BERT implementation back a while ago when the hardware was ready. And we reached, I think, a very high number of 2,800 sentences per second. But that took a few months of manual work, and now you can run through the compiler in 10 minutes and get not only BERT, but many other networks at almost the same performance numbers. Now, obviously, it's not enough for us to come close to that manual number. And just like those early compilers that Ljubisa talked about, they start by producing something that's a bit slower than what a human can do by hand. But eventually, they reach those numbers and start exceeding them by a lot. We've been steadily growing over the last 6 months, and we expect by the end of the year we'll be hitting the same numbers as the hand-tuned demo. And starting in January, we'll be starting to exceed those numbers and go even further. Okay, so when I said I'm not going to talk about conditionals, I guess I lied. I felt that one slide is important to mention here because this is such a key part of the future of ML. We see the models growing at an exponential rate as you get new features added. The matrix multiplies themselves are growing at a cubic rate. And while there are some efforts from everybody out there to introduce sparsity into this picture, linear sparsity and linear gains that you're getting out of such a solution is really not making a dent in that kind of growth. And we feel that with conditional computing, you can create something with chain sparse matrix multiplies that give you a quadratic speed up. And this is really, turning this cubic growth into a linear growth and something that really opens up the abilities of hardware to run new models. Finally, now that we have some software running on many different workloads, we're excited that we're able to share this with potential customers. We already have a number of customers that have our hardware in hand running in their labs, trying out the systems. And we also have an internal development cloud that lets customers log in remotely through VPN and trying out their workloads. We have anything from system builders all the way down to end users trying this out. It's really exciting to finally get our stuff into people's hands. And we were particularly excited about this one piece of feedback from one of the customers that has tried many different competing solutions. And they were truly surprised by how easy it was to install and run our software on their setup. And this is really something we were aiming for, and we hope to deliver on that even further going forward. So to conclude, everybody knows that the new computer architectures are not going to work without great software support. I think we reached a point where we do have that great support. We've achieved generality where we can run almost anything that you throw at it at high performance. And our setup is very pain-free and easy to use. So if you swap in the solutions that you have now with ours, you're going to supercharge your inference and soon training workloads as well. So if you're interested in trying this out, please contact us and we'll work with you to show you what we have. Thank you.